And welcome back to Statistics from Home. If you haven't left your home for a week, congratulations, your country thanks you. Today we're going to review standard error and confidence intervals. We're going to do a few examples. We're going to talk about the relationship between the confidence level, the precision, the standard error, the margin of error, all that good stuff. So we're going to review a little bit of what standard error means and how we build confidence intervals. We're going to do a detailed example, and then we'll talk about how these things work. So let's review. What is the standard error? Statisticians measure things, right? We want to know the average, what's it, or we want to know the proportion of whatever. And so we measure things. How do we measure? We don't use instruments to measure, we use samples. And using our samples, which are like our instruments, we measure a whole bunch of things, but we don't measure everything. And that means that we only get information about a sample when really we want to make inferences about a population. What does that mean? That means our measurements are wrong. Oops, the whole thing doesn't work. Well, it's okay that our measurements are wrong so long as we can control the error, measure the error, and report the error. So long as we have some measure of control over the error that we're making when we measure things by means of a sample, then it's going to be okay. The standard error is exactly that measure. When you measure any feature of a population by using a sample, the standard error is how much error you are likely to make. So if, for example, you're measuring the average mass of a cat and you're sampling a bunch of cats in order to figure out what their average mass is, your answer is going to be wrong. That's not going to be the exactly right value of the average mass of a house cat. But that's okay, because if you can say also, my answer is going to be wrong, but here's how much it will be wrong, and I can report some confidence that it's not going to be wrong more than such and such, then your answer is still usable. Okay, so standard error is super important. It allows us to report the truth. Well, we say the truth, we say how far off it probably is, and then we get usable results. So that's what standard error is all about. The two simplest kinds of standard error are, first of all, the standard error for a mean. If we're measuring an average of something, then that's a mean, and it'll have a standard error. The next most important standard error that we'll talk about is the standard error for a proportion. If we're measuring what proportion of Americans agree with a certain policy, then that will be expressed as a proportion, not a mean, and that will have a standard error too, meaning what we get from our sample will be a certain number, and that number will not perfectly reflect the rest of the population, but that's okay so long as we can understand the relationship between our answer and the right value. So when we measure the standard error of a proportion, then that's the second most important thing. Those are not the only two standard errors that we'll talk about. Eventually we'll talk about the standard error for a difference between two means if we're comparing two populations, or the standard error for a difference between two proportions if we're again comparing two populations by means of the proportion. Whenever we have a standard error, then we have the opportunity to use it to make confidence intervals. And so here I've got the basic recipes for confidence intervals here. We take the measure, whatever it is. I'm writing measure sort of generically. That would be the mean that you measure from your study, or that would be the proportion that you measure from your survey or whatnot. Whatever it is you're trying to measure, that would go there. And then plus or minus the standard error. That makes sense, right? The error is how much you're off. So the value plus or minus the standard error gives you a confidence interval. And that confidence interval tells you, well, the right answer is probably within there somewhere, right? And our confidence level here is 65%. So this much is called the confidence interval, and 68% is our confidence level. Basically, that's how confident we are when we report that measure. Now, the fact of the matter is, if you add and subtract the standard error, quite often the actual value, how much error there really was, can be a little bit more than the standard error. It's typically approximately the standard error, but it could be a little more and it could be a little less. So we don't have all that much confidence that the value is within plus or minus the standard error. And that's why we often widen that interval a bit and go measure plus or minus double the standard error. If we do that, then we can say, well, it's very unlikely that we're going to be off by more than 2 standard errors. So the range of plus or minus 2 standard errors is very likely to catch the right answer within it somewhere. And so we can say with greater confidence that the answer is somewhere within there. And we call that the 95% confidence interval. That 95% is our level of confidence, and that's pretty sure, right? 95% is pretty good. It's not perfect, it's not 100%, but it's pretty good, and we're not likely to make errors if we use that. If we want to be super cautious and we want to make sure that whatever we report is going to be true, then we can triple that standard error, and we can use the measure plus or minus 3 times the standard error. And then we get an even broader interval, and we can say with even greater confidence that the right answer is somewhere within that broader interval. And so we'll get a confidence level of 99.7%. You might notice I put a little asterisk here. This 95% confidence interval is super important because 95% is the typical level of confidence that we want in our statistical results. In most basic situations, 95% is kind of where it's at. The opposite of 95% is 5%. And remember that the typical threshold of significance for a p-value is 5%. So that kind of goes with the fact that we're kind of willing to risk a 5% error in a lot of situations, but we're not willing to risk more than that. So for one reason for that asterisk is because that's really the most important and most standard one, the middle one, where we just take the measure plus or minus double the standard error, and that's the 95% confidence interval. There's another reason for the asterisk there, which is a little bit of a cautionary tale. I don't want to complicate this presentation by doing too much fine print, but there is a little bit of an estimation going on here. This 2, if you want to be perfectly precise, it's not exactly 2. It's rounded off to 2. The exactly perfectly precise number is around about 1.96. But let's not sweat that detail too much. We're just going to use a 2 here. But I bring it up because you might see that in textbooks and things. You might say, oh, to produce the 95% confidence interval, it's plus or minus 1.96 times something. And here I just want to confess that this is a slightly rounded off value here of 2 here. And actually, this 68% is a slightly rounded off value too, but let's not worry too much about the finer details there. Okay, so this is basically how we produce a confidence interval, and I want to do an example. Okay, so the example is going to be a traffic monitoring example. So I want you to imagine that we're monitoring traffic on a road. Now, why would we do this? Well, sometimes you have to consider, is it appropriate to change the speed limit? Or are people generally breaking the speed limit? Or is there some new situation on the road that requires that we need to do something? So if we're making policy that affects the road, then we might want to know how people are actually driving along the road. And we might want to know the average speed at which people drive on the road. Maybe it's a small road and we want to make sure people aren't driving too fast, or maybe it's a highway and we need to make sure that the traffic is continuing to move. So we might monitor traffic on a road. And I want to be definite here about some of the numbers. Let's say that we monitor for one Saturday. So we can't monitor all the time and get every single car, right? That's just not practical. But we could put up a monitor station on a Saturday. Now I want to, just a little side point here. If you're going to monitor traffic on a road because you want to know how people are actually driving on the road, the worst thing to do is to put up one of those flashing signs that reports your speed limit back to you and also has the speed limit, reports your current speed back to you and also has the speed limit on it. Those signs definitely cause people to slow down. And so that would cause a biasing effect to our measurements. We want to put up something that will monitor traffic without influencing the speed at which people drive. If we're really trying to measure something. If we're trying to influence people's behavior, then something else might be appropriate. But if we're really trying to measure, then we should be careful not to influence people's behavior during the measurement phase. So we should put up something, that doesn't really change anybody's behavior, probably something that people don't notice. So we'll monitor traffic for one Saturday. And let's just say I'm going to make up some numbers here that we have 64 cars and they have an average speed something equals, let's say, 35 miles per hour, because that's a pretty familiar speed to us. And I've left a blank here. I want you to think for a minute about what symbol should go there. It's an average, right? So we should use the symbol for an average. And now, after you've thought about that, what are you thinking? Should it be a mu? Should it be an X bar? Should it be something else? There are two symbols in statistics that are standard for an average, and they are X bar and mu. The difference between them is that X bar refers to the sample and mu refers to the population. X bar is a statistic, mu is a parameter. This average is the average measured for these 64 cars, and so that's the sample average, and that's X bar. And we will also have a standard deviation here. And I just tried to make up something reasonable. These are made up numbers. So standard deviation would be, say, 12 miles per hour. What's the proper symbol for a standard deviation? There are two that are typically used. They are S and sigma. Which one is appropriate here? Because this is a sample standard deviation, then we should be using S. So the standard deviation here is S. S is 12 miles per hour. So what does that mean? So in ordinary language, that means that we measured 64 cars. On average, they're going 35 miles an hour. There's about 12 mile per hour variability, right? Cars tend to go 12 miles per hour faster than that, 12 miles per hour slower than that. That's typical. That's kind of a lot of variability here. So we want to use this information to produce a confidence interval. And the first thing you need to notice is that we don't have enough information to produce a confidence interval. The confidence interval is made out of the measurement, whatever statistical measure we produce for that study, plus or minus the standard error. Standard deviation is not standard error. We need furthermore to know the standard error of the measurement. So I'm just going to put that in here, but we can't just do this forever. Eventually I have to teach you how to calculate the standard error. So here I'm going to say the standard error is going to be SE equals 1.5 miles per hour. So now this is where everybody's thinking, what's really the difference between standard deviation and standard error? So standard deviation is the anticipated spread from one car to the next car, one case to the next case, right? The cases are cars driving along the road. So the standard deviation is how much you expect this car and the other car to be different from one another, or rather different from the average, which in this case is 35 miles per hour. From individual car to individual car, there may be a lot of variability, right? Some people are really in a hurry and they don't follow the speed limit and they go really fast, and some people are really cautious. So from individual car to individual car, we expect a lot of variability, and that's why I placed S to be 12 miles per hour here. But that's not what standard error measures. Standard error is measuring how far off we are in the reported calculation of the mean itself. In other words, there is some actual mean among all of the cars. And our measurement of that mean is 35 miles per hour, but that measurement might not be exactly correct, right? We've measured 35 miles per hour as the average in sample, but there definitely are other cars right there in this population, and we haven't measured them all. Now, does it matter? Well, probably it doesn't matter very much. Probably with the sample size, which is relatively large, 64 cars, probably our measured mean is pretty close to the actual mean, which might be 36 or 34, maybe 37, something around there. Probably our measurement is not too far off. And the standard error doesn't measure the variability from car to car. It measures how much variability there is caused by the sampling itself. Remember, we sampled 64 cars. It was 64 essentially at random. Like, there was no particular reason why we chose those. It was just the ones that came that day. If I sample a different 64 cars on a different day, I'm quite likely to get a different average. Even if it's under exactly the same conditions, I'm quite likely to get a different average because there's just some natural variability, and because it's a random sample of 64. It's that effect which the standard error is trying to measure. The effect on the average itself, as calculated from the sample of 64, the effective variability that comes from the fact that the 64 chosen were actually just chosen randomly. Now, that's not going to affect our average very much, but it will have some effect. And so I'm estimating the effect of that to be 1.5 miles per hour. And so let's build some confidence intervals, shall we? So 68% confidence interval, I'm going to abbreviate CI. A 68% confidence interval for this problem would be 35 miles per hour plus or minus 1.5 miles per hour. And we could write that in interval notation. We could write 33.5 to 36.5 miles per hour. So this would be a confidence interval here, going down 1.5 from the mean and going up 1.5 from the mean. That's a confidence interval for the mean. And then we have another confidence interval, which is the 95% confidence interval. And again, a little bit of a fine print. On some technical level, I'm supposed to multiply by 1.96 here, but I'm going to multiply by 2 because it's okay. So that would be 35 plus or minus what? Plus or minus what? I got the standard error here. Plus or minus double the standard error here. 2 times the standard error. And that's going to be plus or minus 3. And so in interval notation, that would be 32 to 38 miles per hour. And then the 99.7% confidence interval, if we really needed to know that whatever we were reporting was very, very definitely true, then the 99.7 confidence interval would be 35 plus or minus 4.5, because I'm tripling the standard error here. Triple 1.5 is 4.5. And that would give us the range of 30.5 to 39.5. Now, notice that that's a very broad range. And so that might reflect the fact that we're really not very, that we're trying to hedge our bets. Basically, what this means is we're trying to hedge our bets. We're trying to make sure that whatever we say about it is definitely true. And by giving this really broad range, we can be sure that saying that the right answer is in there somewhere is definitely true. We can be very, very sure of that. If I give this narrow range, it looks like I'm providing more information, right? That it's in this narrow range. And in a sense, I am providing more information, but I'm much, much less confident about the information that I'm providing, right? My confidence level is 68% here. So let's introduce some vocabulary words for talking about what we're doing here, and then talk about how they relate to each other. So the words that we want to deal with are precision and confidence level and margin of error. Precision of our result tells how tightly or how closely or how precisely we're describing the outcome. You can see that this confidence interval is actually more precise. We describe very tightly this outcome. This one is less precise, and this one is even less precise. The confidence level of the result tells how certain we are that the prediction that we're giving is actually true. You can see here that this one has a confidence level of 68%, which is not very good. This one is 95%, which is pretty standard. And this one is excellent at 99.7%. Now, the margin of error is a confusing term because it's so closely related to the standard error. The margin of the error is how much plus or minus we have to throw in order to produce our confidence interval. In this case, the margin of error is 1.5, which is equal to the standard error. In this case, the margin of error is 3, which is double the standard error. And in this case, the margin of error is 4.5, which is triple the standard error. So you can see, in some cases, the margin of error and the standard error are the same thing. But in other cases, particularly in the standard situation set up here, the margin of error is double or triple the standard error. In this case, the margin of error is 3, the standard error is 1.5. So the margin of error is precisely this value that we get by doubling or tripling the standard error. So these are some vocabulary terms that help us understand what's going on here. Now, how do they relate to one another? As you can see in these examples, we have a kind of a contest here between our goals of precision and our goals of correctness. We're trying to say, I'm really sure of something. And that means we're trying to have a high confidence level. But simultaneously, we're trying to say, I'm going to tell you something really precise. And that means we want to have a narrow result here. And those goals are in competition with each other. If you want to say, hey, it's really just exactly in this narrow range, then you might be less sure of that. But if you want to say it's somewhere in this broad range, then you might be more sure of that. And so that makes sense, right? As the confidence level goes up, then the precision goes down. The margin of error goes up as well, and the precision goes down. So we would like to report everything precisely and confidently, but we can't. We can report things precisely with less confidence and more precisely with less precisely with more confidence. Now, that's true for a given study, given the sample, that these are your options that you have to live with. But that's not true generally. If you have the luxury to redesign and repeat the study, then you can have both precision and high levels of confidence so long as you do the study very well. What does it mean to do statistics very well? Typically, it means to have a very large sample. So if instead of measuring 64 cars, if I measure 6,000 cars or 6 million cars, then I will have an enormous sample. And then what will happen? what will happen is the standard error will just go down. And that's a reflection of the fact that a measurement of 6,000 cars or a measurement of 6 million cars is capable of giving me a lot more information and is capable of measuring the truth much, much more precisely than a measure with only 64 cars. So you can have your cake and eat it too. You can have precision and high levels of confidence so long as the study is very powerful. And the long and the short of it is, if you want a powerful study, then you have to do everything right, including have a large sample. Question: after we build the confidence interval, what does it mean? Let's talk about that next. So you might think it's strange to report that the average speed of a car on this road is 35 plus or minus 1.5. Isn't it strange to report that if we measured the average and found it to be 35? So this goes to the heart of what this stuff means. What does a confidence interval mean? Why are we reporting plus or minus anyway when we just have the measured value right there and it's 35? So the confidence interval is meant to predict the value of mu itself. Now, this is slightly imprecise. We have confidence intervals for means, and we also have confidence intervals for proportions, and we have confidence intervals for other things too. But this is a confidence interval for a mean, so I'm just going to work with the mean value, with the mean here. So the confidence interval is meant to predict the value of mu itself. Notice x bar is 35, but what is mu? Mu is the important question here. Mu is the policy question that's going to drive the decisions for, should we lower or raise the speed limit? Should we put up extra signage? Should we widen the road? It all should depend on the value of mu, because mu is the average generally. This is simply the average of 64 cars, and those particular 64 cars in the grand scheme of things don't matter. It's mu that we really, really need to reason about and care about. And so, but mu cannot directly be inferred from x bar because we know that we have a certain level of error here. So this is the next best thing to inferring the value of mu when you see the value of x bar. What these confidence intervals mean, when we say 35 plus or minus 3, or produce the interval from 32 to 38, what this means, it's obvious that x bar lies within that. X bar is 35. That's not interesting. What this means is that mu itself lies somewhere in there. Now let's remember what mu actually is. Mu is the average over all the cars on this road. And what we're saying here is, I don't actually even know what the average is among all the cars, but I do know that it's somewhere between 32 and 38 miles per hour. That's what we're really asserting there. And when we say I know this, I'm also reporting how confident I am in my conclusion. My confidence level is 35%. Sorry, it's 95%. So what we're reporting is a range of possible values where mu lies. Notice that the individual cars are going to vary a lot more than that. 12 miles per hour down and up from this 35. But we're predicting, on the basis of this study, that the actual average speed of cars on this road might not be 35, but it is some number between 32 and 38. And that might be enough to make the policy decision that we need to make, right? That is enough to say, well, it's more than 30, so maybe the speed limit needs to change, or it's less than 40, so maybe we don't need to add these extra safety controls that we're talking about. So it might be enough to inform policy. It's not a certainty about the value of mu, and it's certainly not right to say mu is 35, right? Because we've calculated x bar to be 35, but mu could be different because it could be wrong slightly. But this is saying mu is possibly different from 35, but it's somewhere within this range. And so we can say that with some confidence. Now, that's what it means. If we're producing a confidence interval for a proportion, then it's not right to say that the mu is actually in that confidence interval, because we would be talking about p then, the population-wide proportion. Or if we're producing a confidence interval for the difference between two means, mu1 minus mu2 or something like that, then the confidence interval would say, whatever the difference between two means is, it's probably somewhere within this range. So whatever we're producing the confidence interval for, it gives us a prediction that applies to the entire population, not just the sample, and it gives us a level of confidence with which we can say that. So for example, if you do a political poll, then you get 54% plus or minus 2%. That plus or minus is typically double the standard error. It's not the standard error for a mean, because if we're doing polling and it's a yes-no situation, we're talking about a proportion there. But it's a standard error for a proportion. And that plus or minus 2% is the margin of error for that study. And when we say that it's whatever, 54 plus or minus 2%, what we're really saying is somewhere in that range from 52 to 56, that's where the actual answer is. That's what the population of the United States is actually like as a whole. Not necessarily 54, but somewhere between 52 and 56. That's what the population of the United States is like as a whole. So that's what the confidence interval means. I want to talk to you next about what kind of effects it accounts for, right? We're trying to account for the variability and account for the possibility of error. So the standard error and the confidence interval, they account for error. And I want to talk to you again about what kind of error they account for. So they account for the randomness, so the error derived from the randomness of sampling. And that's basically what they account for, and that's what they need to account for. So that's the error from the random sampling. So we're going to go out and we're going to measure 64 cars. And if we measured a different 64, it would be different. And a different 64 from that would be different still. So that would cause variability. And the standard error accounts for that level of variability. I want to emphasize that they do not account for errors caused by the method of statistics, and they do not account for errors caused by bias. So they don't account for bias errors, and they don't account for design errors. They don't account for instrumentation errors. So let's talk about what those might be. So in the context of this monitoring the road example, what would a bias error be? Well, it would be this choice, for example. If you measure the cars on the road on a Saturday, then you're likely to get a different population than if you're measuring them on a weekday. You may get fewer cars, more cars. I don't know what would happen. Maybe they drive slower or faster. But the weekday, weekend phenomenon is probably going to affect the traffic on the road one way or another. And so the choice to monitor the traffic on one Saturday only is probably going to introduce bias. The cars are going to be driving slower, maybe faster, I don't know, but it could introduce some bias during that day. And so that could be a potential problem. The standard error and the confidence intervals built from the standard error cannot account for that. They just can't see that bias. Maybe all the drivers drive slow on Saturday, but they always drive fast on the weekends. On the weekdays. There's no way that the data can help us account for that if the data is biased. If we design the experiment wrong, there's no way that the standard error and the confidence intervals can help us account for that. They can help us account for the error that derives from the fact that sampling was random. Samples always should be random, but that randomness introduces error, and the standard error can account for that. They cannot account for bias, and they cannot account for design errors. They also, of course, cannot account for instrumentation errors. If this, whatever device we're using to monitor those cars, if that device is measuring their speeds wrong, then there's nothing that a statistician can do to fix that, right? What could you possibly do with the data to fix the fact that the device is reading it wrong? So if you've got instrumentation errors, there's nothing a confidence interval can do. And moreover, if the instrument is malfunctioning in such a way that causes bias, for example, maybe the instrument can't catch and can't read the speeds of cars going faster than 50 miles an hour. well then it's going to exclude them from our sample accidentally, and that's obviously going to cause a bias towards the slower cars, right? We're only measuring the slower cars and not measuring the faster cars. So that's going to cause our sample to be biased and wrong, and that would be an instrumentation error. And there's nothing that the standard error or the confidence interval methodology can do to fix that problem. It just would just get the wrong answer. So the thing that it can do is it can correct the it can account for the problem of the randomness of sampling, and that's basically it. Now, we've talked about, how important the standard error is, right? The standard error allows us to produce the 3 margins of error, which allow us to produce the 3 typical confidence intervals, which allow us to make statistical inferences and say what the population is like. That's so super important that every pollster and every statistician has to be able to produce these confidence intervals from the standard error. But what have I left out? I haven't given you a way to compute the standard error. And of course you have to compute the standard error if you're going to make any of this happen. So here, I'm just handing it to you. It's 1.5 miles per hour. But where did that come from, right? How could you possibly know that? Do I have to do a whole bunch of identical studies and then see how they're sorting out? Well, the good news is no. You don't have to do a whole bunch of identical studies in order to figure out what the standard error is. You just need to know the right formula. So I'm going to tell you the right formula for the standard error. Now, as I mentioned, if you're measuring a mean, you get a standard error for the mean. If you're measuring a proportion, you get a standard error for a proportion. If you're measuring a difference between 2 proportions, you get a standard error for that. And so there are actually a lot of different formulas for the standard error. But we're going to do the 2 most simple formulas first, the standard error for a mean and the standard error for a proportion. So the standard error for a mean looks like this. So the standard error is equal to the sigma divided by the square root of n. And now maybe you're thinking, what on earth is sigma and what on earth is n? And that's the glory of having standard notations for things in statistics that always mean the same thing. This is a little n, not a capital N. And so that means, the fact that it's an n means that it's a size. The fact that it's a little n instead of a capital N means that it's a sample size. So, where n equals sample size, what is sigma? Should I explain what sigma means? In theory, you're supposed to already know what sigma means because it's a standard notation in statistics. Sigma means standard deviation. That is not enough. Which standard deviation? Sigma means the standard deviation which describes the population generally. S would be the standard deviation that describes the sample. So sigma is a parameter. It's the parameter version of the standard deviation. So that's a population standard deviation. Standard deviation. Putting sigma together with root n will give you the standard error. Now, since we're doing formulas here, I want to do the standard error for the proportion next, but this is the one that we're going to be using in this lecture. So I just want to have them together. So the standard error for a proportion, is going to be the square root of p times 1 minus p over n. And so let me talk about what that means. N is, of course, the sample size. So n equals sample size. And p is the proportion. That's kind of funny that the proportion itself shows up in the formula for the standard error of the proportion, but that's how it works. Notice that it's p, not p hat, and that means that this p is the population proportion as well. So, we'll come back to this formula later. You have it here. I'm going to erase it, and we're going to use this formula to showcase how I got the standard error for the mean over there. So we'll come back to this. And you'll see a devilish little cheat if you watch closely. So the standard error for the mean is going to be sigma over root n. That's the standard deviation over the square root of the sample size. Now, if we go over here to these numbers, the sample size is 64, which is a number that I chose so that I rigged it so that the square root will be easy to calculate, and that's 8. What's the standard deviation? The standard deviation we can measure from the data. The data, once you get the data set, then you can measure the standard deviation from the data set using whatever tools you need. So the standard deviation can be measured from the data, and that's 12 in this example. So we get 12 over the square root of 64, which is 12 over 8, which is 1.5, and that's how I got the standard error to be 1.5 in the original example. This is critical that we know how to do this. Once we collect our data, it's easy to calculate the average speed, the average. It's easy to calculate the standard deviation from the data set. We know how to do that. If we're using Colab and Pandas, we do df.describe on that data frame, and it's good to go. If we're using Excel or Google Sheets or something, then we just do equals average and equals standard deviation. So those are easy to get from the data, but we also have to have the means to get the standard deviation from the data. And this is how we do it. We take the standard deviation, and we divide by the square root of the sample size. And now I said if you watch closely, you see me cheating, and I did cheat. Do you see it? I plugged in 12 for sigma because 12 is the standard deviation. Well, sigma is the population-wide standard deviation, and 12 is actually the value of S, which is the sample standard deviation. Does it make a big difference? Probably not, because probably the sample standard deviation is very close to the population-wide standard deviation. But maybe. Probably not, but maybe. It's possible that S is different from sigma. And we have not accounted for that possibility here. So this introduces a slight inaccuracy. Should we do better? Well, yeah, in principle, we should do better. But notice that sigma itself is the population-wide standard deviation. And if I'm not measuring any more than 64 cars, I can't possibly know the population-wide standard deviation. There's nothing I can do to get the value of sigma. So I just have to do the next best thing. I have to use S as an estimator for sigma as I do this. And it might be slightly off, but that's the best that I can do. So this is the best we can do. To plug in sigma. It's the only thing that we can do because we don't actually know the value of sigma, but we do know the value of S, and it's probably pretty close, and so we'll plug it in. And so that's how we get the standard error. So if you think about this from a forward-moving point of view, just like starting from the data, if you start from the data, you can calculate the average. Starting from the data, you can calculate the standard deviation. Continuing with the standard deviation in place of sigma, you can apply this formula. You know your sample size. I hope you know your sample size if you did a study. You don't know your sigma, but you know the next best thing, which is S. So plug it in here, and you'll get your standard error. Then on the basis of the standard error, you can find the confidence intervals that you need. Probably you need one of these and don't need the other two, but I don't know which one you need, so I'm providing them all three of them. Double the standard error is the margin of error here. Triple the standard error is the margin of error here. You make your intervals and you declare, ultimately, the true average, the mu, the actual average speed on the road is going to be, perhaps you choose this one, is going to be somewhere between 32 and 38. So all of this you can do starting from your data if you know what's up. Notice the importance of the formula for the standard error for producing our confidence interval. Now, as I said before, if you want to improve your results, you can improve your precision, but at the expense of your confidence level. You can improve your confidence level at the expense of your precision. If you want to have the best of both worlds, then you can improve your study itself by increasing the sample size. So I want to indicate what happens here if we increase the sample size. And I want to do something where just hypothetically, I'm going to change the 64. Now because I have a point to make, I'm going to quadruple that 64. And what's quadruple 64? That works out to be 256. So I'm going to recalculate what would happen if we did a larger study. So larger study, this is a hypothetical, but if we did a larger study with 4 times 64, which is 256 cases. Now what would happen? Well, in a larger study, if we repeated the study, we might get a slightly different mean and we might get a slightly different standard deviation. But let's just say for the sake of argument that we got the same numbers back for those. then we would have the standard error, which would be sigma over the square root of n. And that would be 12 over the square root of, now for n we will use 256. Now, the square root of 256, maybe you don't have it memorized, but you know me. So I have it memorized and it's 16, right? So that's 12 over 16. And then 12 over 16 as a fraction is, well, it is a fraction, but it simplifies to 3/4, which is equal to 0.75 in decimal. The important thing to notice here is the relationship between the standard error of the small study of 64 and the standard error of the large study of 256. 3/4, or 0.75, is exactly half of 1.5. And this is a phenomenon that always happens if you increase your sample sizes. If you quadruple your sample size, then you have your standard error. So quadrupling the sample size cuts the standard error by 2. So it halves the SE. Now having the SE, cutting the standard error in half, is very good news for any statistical study, because basically you're saying half the error, right? That's really good. So, but it comes at the cost of you have to quadruple the sample size. So it's all because of the behavior of this square root here. Basically we're multiplying by 4 inside the square root, but that 4 factors out of the square root and becomes a 2. And so the standard error gets cut by a factor of 2. If you multiply the sample size by 100, then that 100 inside the square root factors out and becomes a 10. And the standard error will drop by a factor of 10. So in other words, if I had 64 cars and ended up with a standard error of 1.5 miles per hour, then I could multiply that by 100 and I could do 6,400 cars, 6,400 cars. And then the standard error would not drop by a factor of 100, but it would drop by a factor of 10, which is not too shabby. And we would end up with a standard error of 0.15 miles per hour. 0.15 miles per hour is almost nothing when it comes to traffic laws. And so, so we could basically report as much confidence as we needed. We would have like as good information as anybody could hope for if we had a standard error of 0.15. So the standard error does depend on the sample size, but in this slightly tricky way that if you quadruple the sample size, you have the standard error. If you multiply by 100 the sample size, then you cut it by 10. If you want your sample to be smaller, if you quarter the sample, then the standard error will double, which is something we usually don't want to do because, you know, better statistics comes from larger samples. So this is the relationship. This really sheds a lot of light on the relationship between the sample size and the standard error. And it's just all another part of the basic principle here that if you want good statistics, then you have to have large samples, right? If you want good statistics, then you probably want small errors. And without control over sigma, the only thing left here to control is n, right? If you want this to be small, you can't change this value because that's a feature of the population. The only thing you can change is that value. And if you want this thing to be small, that thing has to be big. So it's just all another part of the principle that good statistics happens when the samples are really big. Thank you.